Hey, what's up, guys? This is Cheng here. So today, let's take a look at 546 remove boxes. I think it's kind of difficult DP problem. Okay, so you're given like several boxes with different colors represented by different positive numbers. So each number represents a color, and you can remove any of the boxes, okay, until there's no box left. So each time you can choose some continuous boxes with the same color, and then after removing that colors, you get the k times k point, and it asks you to find the maximum points you can get, right? So for example, this one, and so we have like this three twos together, right? So basically, if at the first round we remove any of the two here, we remove any of the two here, since we have a three twos uh, are together. That's why in the first round move, we got 3.3 points, right? And after removing the three twos here, we ended up like this one here, right? And then the next round, we're removing four here, right? So by removing four here, we get 1 times one. And then the next time we have like this three threes together, and by removing those three numbers, we get 3.3 again, right? In the end, we have two ones together, and then that's 2.2, right? So in total, we have 23. That's how we get this number here. All right, and then we have several boxes. The length is it's not that big, only 100, right? So then so to solve this one by using DP, I mean, at the beginning, someone may we might start thinking about DP I and J, something like that, right? So I and J means that starting from I to J, right? What's going to be the maximum point we can get, right? From starting from I to J, okay? But if you read the descriptions again, right, or carefully, you know that, right? So by giving this I and j, we don't know. Like let's say if the I and j is here, let's say if the I and j is 2 to 3, let's say this is the I and j. We cannot simply do a like a check, right? Only within the range of I and j, because since we have 2 here, we have another 2 before I here. And if we only check the string the array I and j here, we see two twos here, right? So we're saying okay, so by removing any of those two, we will get 2 times 2. But it's not right, right? So by removing any of these 2 and 2, we are getting actually 3.3 times 3. It's not 2.2. So then it means that I and j is not enough. So which means we have to introduce a third dimension to help us solve this problem. So I mean, I think we have already seen a potential candidate for the third dimension, which is the like how many numbers, the same numbers that's I mean is the same as the current I. So I'm gonna call it I and J and K here. So K means they're like uh, they're like K numbers. K's same color, right? As I. Right? So for example, this one, we have I and J here. So which means so the DP I and J and the K is that basically the K will be 1. It means that before I, there is a one additional 2 before I. So that that can help us like get the correct numbers by removing off the numbers here. Right? All right, so once we have that, the actually, and if we have the definition here, and then the next thing we need to figure out is the state transition function, right? And actually, that state transition function is even trickier than the state definition itself. So, and I'll give you some examples here. So let's say I'm drawing like examples here. Let's say 1, 2, 2, 2, 3, 4, 3, 4, 2, 2, 1, 3, 4. All right. So, and let's say we have a I and j, and let's say I is here, right? Let's say I is here, and j is here. How about that? Okay. So let's say there we are trying to calculate this I and j. So I mean, when we trying to come up with the state transition functions, we always try to split, I mean, the current problem into a smaller size of problem. That's how this DP works, right? And by given like it's I and j, and by given like there is case same numbers before I, how can we split these numbers into the smaller version of number? That depends on like basically we're trying to see how many like between I and j, how are we going to remove the numbers, right? Actually, if we if we're going through this examples a few more times, we might already find out actually there is a strategy here, right? Basically, we're trying to get okay, we're trying to make this the same numbers as big as possible. That's why when we're at this state here, we're not removing 3 and 3, but we're removing 4 here. Because after removing 4 here, we'll have like 3 and 3. We'll have 3, 3 together. That's why then it's gonna guarantee us to get a bigger number, right? So basically within each of the state here, we do have like a greedy approach here. So what's gonna be the greedy approach? Actually, there are two ways of doing there are two options. The first option is to remove the current one, the current I, until we are reaching the a different numbers. So which means that, for example, this one I and j, the first option is which will be basically we're trying to remove we're moving the i's until we have like we encounter different numbers. Then we have the total counts, right, of 3 here. So that's gonna be our first options to remove, right? That's gonna we remove this part until we have reached encounter a different number. And the second options or other options is to remove what? Is to remove uh we just keep going to the right side until we have find I mean after we have find this location, right? We're going through the right until we reach J, and we'll find if there's like another 2 on our way, right? So for example, if we have this number, let's say the current I is here, right? After finding after moving to the right until we reach a different numbers, right? And then we're going through to the right side until we find another a 2 here, right? So let's say this M here. So why is that? Like I said, right? I mean, it's because we're trying to remove this part. After removing the parts in the middle, then we'll have like a longer tooth, because we have already have tooth here, and by having another two here, right? Basically we're increase the next point, the next length up by after removing this 3 4 3 here. So, and that's going to be our second strategy. Basically, every time when we see another like 2 here, we will try to remove anything that's in between so that we can have like a different the next one, so and with a longer 2 here, with a longer length of the same number, then actually the state transition function will be like this, you know. So let's say we have like the dp, right? So dp I, j, and k. So I'm going to type it here. So basically the dp I, j, and k, right, equals to what? Equals to the so the first option is this. We have like we need to remove this one first, right? That's gonna be the dp of what? The I say II, right? So let's say we have a this is II, right? After going through this the first while loop here, so we have dpii and then j, right? And then equals to 0 because after removing after removing this part here, we have like we have 3 here, right? So which 3 means that there's nothing before 3 because remember we have already removed everything that's outside of I and j. So even though we have a 3 here, you know, but the 3 was already gone, right? So it will not affect the 3 here. That's why after removing this, after removing anything that's before this I and I, we have dpii j and 0 plus what? Plus a count, right? Count uh, the power of 2. So that's the first. That's the first option. And the second option is that we have from here, from the II until j here, we'll try to find another number that has the same number as the 2 here. That's why we're gonna have like what the dp I and j. Another one is like the dp of I, right, to what? To m minus 1 and then 0, right? So if we decide to remove anything, if we decide to remove the thing in between the I and M here, basically we have then it's going to be another small sub problem, and the starting point is I and I here, right, and the ending point is M minus 1, right, because we want to keep the current M here because it's the same number as a 2 here. That's why the starting point and the ending point is I and I and to the n minus 1. And the same thing, right? So for this kind of sub problem, you know, it's also like still the 0 because 3 there's no more 3s before the current I here. That's why that's that, right? And what the other one's the that's something that's after anything that's after this one, right? So what do we have? We have uh let's see, what do we have? We have like the dp starting from m, right? Starting from m to r, and then it's a k plus the count, right? So you know this part is also kind of not too difficult to understand, right? So basically we're starting from m, and then we are like until to this j here. Sorry, this is j. This is j, right? So why is that? Because now we only need to consider in this part because after removing this the part in the middle, we know that you know that we have like from here to the left we have like k plus count number of twos, right? On the left side. That's why we can basically and convert this part into our definition again, right? So now we have starting from m to j, right? And but the count is basically the k plus count. So that's why we convert we split this I, j, and k into a smaller version of problem, and that's how this dp will work. And after figuring out all this kind of DP state transition function here. I think all is left is just some implementations. So okay, so let's start doing that. So we have DP, we have I and J, we have a K, right? So same thing, we're gonna use this Python's built-in cache functionalities which can save us a few lines of code, right? And then in the end, we simply do a start from 0, and the length is the endpoint is the length of boxes minus 1, right? And then at the beginning, k is 0, right? So, and okay, so let's do a, hmm, let me think. And I'll do I equals to I here, so that we can keep this I later on, or we can use the same thing, but I just want to make them like separate. So like first, we find the consecutive consecutive numbers, right? From I, starting I, right? And we have a count equals to 1 and the I plus 1, right? So that's the beginning because we want to do a while loop here. Anyway, I mean, there are like different ways of doing this while loop here, but this is just my way of doing it. You can just do it your own way. It's fine. So while LL is equal to the same of R, right? That's the and the boxes of II equals to the boxes of the II minus 1, right? So if that's the case, we do II plus 1, and then we do a count plus 1, right? So that's that. And now, so the first option, right, option 1, right, is to remove the current number, the current ith number, right? And the way of doing it is going to be a dp of the ii to the right, right? After removing the current ith numbers, we have this ii, right, to r, and then we're going to be having a 0 of the case, and plus k plus count, we do a power by 2, right? Because by removing the current I here, it doesn't really matter because we don't have to try the other ones, try anything between the I and II because they will give us the same result. That's why we are only removing the current ICE number, right? And by removing the current ICE numbers, the remaining part will starting from the I and I, right? And then it will be ending to the right side, to J here. Okay, I think I'm using this J here. And then the points we're getting by removing the current ICE number is this one. Okay. And then the option 2, right? Option 2 is to find the same number, right? Starting I and I. Okay, so now we have for m in the range of I, right, to the j plus 1, right? And then if the boxes of the m is equal to the boxes of I, right? It's because I is the numbers we're trying to look for, right? If that's the case, right? So we do a max of answers of the so the first one is by removing anything in the middle, right? It's gonna be the I, right, to m minus 1, right? That's something in the middle. So remember we have this kind of 1 3 2 2 2, right? 3 4 3 2 2 1 3 4, right? So let's say we have an I here, this I, I'm drawing this one more time just to make sure you understand the state transition function here. So let's say we find another 2 here, right? That this is going to be our middle here, right? So the second the options we're doing right here is that, okay, we decide to remove this part, 3, 4, 3, which is the I to n minus 1, and then the k will be 0, right? So, oh, sorry, I have to do a dp here. It's not, it's the, we're doing like the top down. So, okay, this is the j and 0, right? So that's the first one. And how about that's the left? Anything left is the m to j, right? It's going to be dp of m to j, and the count will be k plus count, right? And then yeah, there you go. That's it. And then in the end, we simply return the answer. And don't forget to do a base case. So the base case is if the I is greater than j, right? We return 0, which means nothing. Yeah, I think that's it. So if I run the code, yeah, accept it, and it's accepted, right? So yeah, I mean, so that's pretty much it is. And time and space complexity, right? So for the time complexity, we have I and j. You know, let's say we have an n here, right? So the I and j, they are both like the possibilities for ij and k. I think that's n to the power of 3, because we could have 100 different I, 100 I, 100 j, and what for each of the I and j, we could have a different uh, number, 100 up to 100 different possibilities that have like a same numbers of I. That's why the for this dp and I for the state we have n to the power of 3, and then within each of the dp functions here method here we have uh, yeah, basically we're doing like a for loop here, right? So we have a n here, and then we have another n here. Yeah, so in total, it's going to be a n to the power of 4. That's going to be the time complexity of that, right? And for space complexity, it's the state of the dp, right? It's going to be the O of n to the power of 3. Yeah, cool. Yeah, I think that's it for this problem. And yeah, I think this is a pretty hard DP problem, especially, I mean, especially you have to come up with a third dimensions. And after the third dimensions, you also need to somehow come up with, I mean, the first option is kind of straightforward, but for second options, you have to be able to find the pattern, right? So it's a little bit of greedy approach here. We only trying to remove the things in the middle if we find another match for the current ice number, right? And then we just keep doing it until we find the max number. All right, cool guys. I think I'll just stop here. Thank you so much for watching this video and stay tuned. I'll see you guys soon. Bye bye.